In this lesson, we're going to talk about the magic derivative shortcut, which is just another way of saying logarithmic differentiation. Okay, that took a second to write. Alright, so by the end of this lesson, you should be able to answer the following little question. What is logarithmic differentiation, and how can this make finding complicated derivatives easier? And by the end of this unit, you should be able to answer the following big questions. How do we make finding derivatives easier, and what is the point of finding derivatives? So we're still kind of in big question 2 at this point, but the last 3 lessons in this unit will be some more applications that kind of give us the answer to what is the point of finding derivatives. So let's do the warm-up. So we're going to review some logarithm rules below. So first, if we have the logarithm of a product, that's going to be the sum of the logarithms. If we have the logarithm of a quotient, that will be the difference of the logarithms. And if we have the logarithm of something raised to a power, well, that's just the power times the logarithm. So we have b times ln of a. And so I think a lot of students have trouble with logarithms, but I was always taught that logarithms are just exponents. So if you kind of think about rules of exponents, these laws of logarithms make sense. So you know that if you have two things multiplied together, then you add the exponents. If you have two things divided, then you subtract the exponents. And if you have like an exponent raised to another exponent, you multiply the exponents. So thinking about logarithms as exponents helps you to remember these rules, I think. So think about that for a second. Okay, so what have we done up to this point? Well, we've learned how to differentiate nearly every type of function. So we've done sums, we've done products, quotients, constant multiples. We've even done implicitly defined functions. But we do have some issues. So, for example, let's say I gave you this function right here. Well, that doesn't look very nice, okay? So, you know, you're probably watching this video by yourself, but think about briefly how complicated, if you saw this function, how much would you or would you not want to take its derivative? Me personally, I would probably ask, is there a shortcut? Because I'm looking at this and I'm thinking, oh man, there's 3 things multiplied together on the top and 3 things multiplied together on the bottom. So those would each need 2 product rules. And then you've got a quotient holding the whole thing together. Then on top of that, you got multiple chain rules. So this thing is just disgusting. But I'd be willing to do it if there's a shortcut. The other issue we have is, what if we were given something like y is equal to x to the x? Well, we couldn't use power rule on this because the variable is an exponent, but we also can't use the power function rule. So like we can't use n times x to the n minus 1, and we also can't use, a to the x ln a. So we can't use both of these because this type of function doesn't fit into either category really, because notice here we need the base to be a variable and the exponent to be a constant, which we have the variable a base, but we don't have a constant exponent. And then if we look at the second type I wrote down, so those power functions, here we need a variable exponent and a constant base. And so we have the variable exponent, but we also have a variable base. We don't have a constant base. So both of those rules don't work, so we're going to need some other strategy to tackle these. So this is what motivates logarithmic differentiation. So this is our final method for finding derivatives of functions. So now that we've learned this, or after you finish this video, you should be able to take the derivative of like basically any function that you could possibly be given. So just to summarize, this might help you when you're working through some homework problems. Basically, logarithmic differentiation boils down to a few steps. So I'm not going to go over those right now because I think it's better to just see it in action, but these are here for you to reference when you're working on problems. Okay, so let's dive into a couple of examples. So for our first one, we're going to find dy dx if y is equal to x to the 3/4 times the square root of x squared plus 1 all over 3x plus 2 to the 5th. So the first thing we're going to do is take the natural log of both sides of the function. So this is going to give us ln of y is equal to ln of x to the 3/4 square root of x squared plus 1 all over 3x plus 2 to the 5th. All right, so step one, super easy. We basically just write ln on both sides of the equal sign. Now it gets a little trickier. So now is where we want to bring our logarithm rules into play and simplify the right side of this as much as possible. And by simplify, it actually doesn't mean simplify. We're actually trying to expand it as much as possible. But what that's going to do is simplify the derivative. So maybe I'll make a note of that in a different color. So simplify our derivative. And you'll see what I mean once we get this expanded out. Okay, so first of all, I notice this is a quotient, and I have a product on the top of the quotient. So the first thing I can do is I can, actually let me write this higher up in case I need to do a second step. So I can split this up as ln of x to the 3/4 plus ln of the square root of x squared plus 1 minus ln of 3x plus 2 to the 5th. Okay, now, so I've used my multiplication and division rules. Now I want to use my exponent rule concerning logarithms. So the next thing I'm going to do is all of those exponents I'm going to pull out of the logarithms. So the first one, we can pull the 3/4 to the front, so we get 3/4 ln x plus, now that square root is actually an exponent of 1/2, so I can pull a 1/2 to the front, and I have 1/2 ln of x squared plus 1, and then I can pull that 5 to the front as well, so I have minus 5 ln of 3x plus 2. Okay, and I think that's about as expanded as I can get, because this exponent of 2 we can't pull out to the front because not everything in that argument is raised to the second power. So, oh, that was more than I bargained for. Okay, but anyway, I can't move the 2 because, yeah, not everything is raised to the exponent of 2. So this is as far as I can go. So our next step in applying logarithmic differentiation is to differentiate this implicitly, okay? And so now is where you're going to see that even though we had to expand it out a lot, it's going to make the differentiation a lot easier. So that was what we meant by simplify our derivative. Okay, so first of all, we differentiate the left side. So we have the natural log of y, derivative of that is 1 over y. But I have to multiply by y prime. And then I have 3/4 ln of x, so that's 3/4 times 1 over x. Next, I have 1/2 ln of x squared plus 1, so that's going to give me 1/2 times 1 over x squared plus 1 times 2x. So I have that chain rule in there. And then I have minus 5 ln of 3x plus 2. So I have minus 5 times 1 over 3x plus 2 times 3. And that's my derivative. So notice how nice taking that derivative was once we expanded it out using logarithms. So basically all we had was a couple of chain rules and the derivative of a logarithm. We never had to do product rule. We never had to do quotient rule. So personally, I think this strategy is super, super nice. But we're not quite done yet, so let's solve explicitly for y prime and also simplify just a little bit so that our answer looks nice. And we need to practice that anyway. Okay, so let's see. What do I want to do? Well, I could say, well, actually, let's just rewrite our answer over here. With the y moved over, well, no, let's just rewrite it. Okay, so we have 1 over y prime is equal to 3/4 times 1 over x plus 1/2 times 2x over x squared plus 1 minus 15 times 1 over 3x plus 2. Okay, let's see. From here, the most important step is to take this 1 over y and multiply it to the right side. So in doing that, basically what's going to happen is we're going to get y prime is equal to y times all of the stuff that we got with the logarithms. So now I'm going to simplify this stuff a little bit. So we have 3 over 4x plus the 2's in the next term cancel. So we have x over x squared plus 1 minus 15 over 3x plus 2. All right, and so our last step, we want everything in terms of x, so our last step is to plug back in the function y. So I have y prime is equal to x to the 3/4 square root of x squared plus 1 over 3x plus 2 to the 5th times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. All right, and so this is our derivative of the function. And I probably should have written that as dy dx, but let's see. Could I do it really quick? Yeah, I could. I haven't written too many of these. Okay, so I'm going to replace all the y primes with dy dx's just so we practice that notation. Okay, so we have dy dx, dy dx, dy dx, and dy dx. Okay, so that's our first example. Let's try one more. So we're going to have this exponential form this time. So we're going to differentiate y is equal to x to the square root of x. So first step, just like the last problem, we take the natural log of both sides, which just means we write ln on both sides. Easy peasy, lemon squeezy. All right, let's expand as much as possible. So we can't really do much to the left side, but on the right side, I can bring down the square root of x. So I have the square root of x times the natural log of x. Okay, so now we want to differentiate implicitly. So in the last problem, you were probably thinking, oh, great, we can avoid all the product and quotient rules in the world. But it turns out that we can't avoid them forever. So in this problem, we are going to need a product rule, but we still get to avoid quotient rule, so it's not too bad. So if we're differentiating implicitly, the derivative of ln of y is 1 over y prime. I'll use prime notation here because I didn't specify which to use. And that's equal to, on the right side, we're going to need the product rule. So we start with the square root of x times the derivative of ln x, which is 1 over x, plus the derivative of the square root of x, which is 1 over 2 root x, times ln of x. All right, if you're still struggling with the square root, make sure you convert it to a power and use power rule, and then you should get what I got here. Okay, last step, solve explicitly for the derivative. So let me rewrite my previous step just so it's not confusing where it comes from. So we have square root of x over x plus ln of x over 2 root x. Let's see. So I can multiply over the y. So I have y prime is equal to y times root x over x plus ln of x over 2 root x. And really all I can do here to simplify is divide root x by x and plug in the y. So we have y prime is equal to x to the square root of x times 1 over root x plus ln of x over 2 root x. And that is my derivative. Okay, so hopefully you found that logarithmic differentiation is actually not too bad of a method for doing derivatives. So it seems like it'll be complicated at first just because of all the log rules, but I think in the end this method is really, really nice. So you might consider giving it a try, and we're going to do it in the recitation anyway. But last thing I want you to do is just make sure to check your understanding. But that is the end of lesson 14.